Welcome to second semester. Unit 6 is all about square roots and cube roots. It's kind of the radical unit is what we call it. We're going to start off with some real pretty basic review of square roots and cube roots. So it's to simplify. So on this very first one, simplify the square root of 49. Now, just a couple things to remember. The index of the radical, when you don't see it, it is a 2. So sometimes you might see it there, but when you don't see it, you know that that's a square root. Now, the reason it's important is because that index tells us how many times something has to group up for one of them to be able to come out of the radical. Which is real quick. We all know the square root of 49 is 7. But the reason it is because if we factored out, if we did a factor tree of 49, we'd have 7 and 7. And then by the definition of square root, anytime you find 2 of something, they get to group up and one of them gets to come out. And so that's the reason the answer is 7. Okay, that's the principal square root of 49 is 7. Now, the cube root of 8, let's do the same thing. Let's factor tree the 8. So we got a 4 and we got a 2. The 4 can go down further to 2 and 2. Okay. Now, we have taken that 8 down to its prime factorization. Now, because we're working in cube roots, we're looking for groups of 3, and sure enough, we found it. Here's a group of 3 2s. So by definition of the cube root, one of them gets to come out, and that's our answer. Now, the square root of negative 36. You know how to take the square root of negative 36 if you get to use the imaginary I. I equals the square root of negative 1. Okay. But you also first learned that you can't take the square root of negative 36 if you're only dealing with real numbers. So, if you are only dealing with real numbers, the answer is empty set. You can't take the square root of negative 36. But if you're able to use imaginary numbers, then we're going to use I to take the square root, to take the negative out of the square root. So that would be I square root 36. And then we know the square root of 36 is 6. So the answer is 6I. So depending on whether you get to use real numbers or imaginary numbers, there could possibly be 2 different answers. You just have to know, are you restricted to only the real numbers, or do you get to use imaginary numbers? Now, cube root negative 64, that's a totally different ballgame. The negative is not hurting us at all in the cube root of negative 64. Because I can do this, I can factor tree this down to positive 8 times negative 8. Now, the positive 8 can be factor tree down into 2 times 2 times 2. That's something you're going to want to remember. The cube root of 8 is 2. 8 is 2 times 2 times 2. It's going to save you a lot of time throughout this unit. Now, how about negative 8? Well, negative 8 is negative 2 times negative 2 times negative 2. Because negative 2 times negative 2 is positive 4, but positive 4 times negative 2 is negative 8. So what have we found? We have found a grouping of 3 2s, so we get one of them. We've also found a grouping of 3 negative 2s, so we get one of them. So the negative 2 times the positive 2 is negative 4. So the cube root of negative 64 is negative 4. And the only thing you have to do to check it is, what is negative 4 times negative 4 times negative 4? And it's negative 64. Okay, let's work on one that isn't a perfect cube. The cube root of negative 32. First of all, remember, this can be done. It's not necessarily, the empty set. So let's take negative 32 and prime factor it. And one way we can prime factor it would simply be take that negative 8 that's in here and multiply it by positive 4. Now, for that negative 8, we already know what negative 8 can do. Negative 8 can do negative 2 times negative 2 times negative 2. We just figured that out in the last problem. The cube root of negative 8 really is negative 2. Now, what about this other 4? Well, that 4 can be broken down to 2 times 2, but remember, we're working in a cube root. So in order for something to be beneficial to us, we need to actually be able to find 3 of them. Well, so all we have as the answer is the negative 2 that came out. Go back to red. The negative 2 that came out and the cube root of positive 4 that stayed in. And that's the answer. Now, how about the square root of negative 50? That's where we need to remember if we're dealing only in real numbers, there is no answer. Okay, it's the empty set. But if we can use imaginary numbers, it would be I square root 50, and 50 is 25 times 2, and 25 is 5 times 5. So here's your pair of 5s, because remember we're working in square roots again. So a 5 came out along with the I, but what didn't come out was that 2, because it didn't have anything to pair up. And so there's your answer. Or there's your answer, depending on whether you are restricted to only dealing with real numbers. Okay, now I'm going to get into something that you probably haven't experienced with squares, square roots, and cube roots. The idea of what if you're square rooting a variable? Well, first of all, on this problem, the square root of 36x squared. Okay, again, we know the index of the radical is 2. Whether or not we actually see it or not, we know the index of the radical is 2. So we know a 6 is definitely going to come out because the square root of 36 is 6. The principal root of 36 is 6. But that takes us now to the x squareds. Well, anytime you square anything, you will get a positive answer. So that means whatever this is positive, and it's capable of being square rooted, unlike the ones that were negative and we had to use imaginary numbers. So we're just going to say we know this is a real number. Okay? So anything squared is positive. So x may have started off to be positive in the first place, where positive times positive would stay positive, but it may have started off as negative, because when you take something that's negative and square it, it becomes positive. And once it becomes positive, it's capable of being square rooted. So we know 6 comes out, and x squared is simply, if you factor treat it, it's x times x. And sure enough, there's a pair of x's, so one of them gets to come out. However, we don't know whether it was positive or negative in the first place. So what we do to make sure we take care of that situation is we put absolute values around the x. And what that does is it guarantees us now that regardless of whether it was positive or negative, it's capable of being square rooted. So that would be the answer to this problem. 6 absolute value x. Now, in the next problem, we're cube rooting. Well, the idea is you can cube root a positive number, but you can also cube root a negative number. We figured that out on this problem right here, which was the cube root of negative 64, and the answer was negative 4. So I don't have to worry about whether this started off as positive or negative. So if I break down 48, 48 is 12 times 4, 4 is 2 times 2, 12 is 4 times 3, 4 is 2 times 2. So since I'm dealing with cube roots, I'm looking for things that will group up into 3. And sure enough, there's 3 2's right there. So one of them can come out. Now, how about x to the 6th? Instead of making a factor tree, I'll do it like this. X to the 6th is simply x, 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 x. Now, in groups of 3, here's another group of 3, and here's another group of 3. So I get to take one out, and I get to take another one out. So x times x is x squared. So the 2 came out, x squared came out. Now we have to figure out what stayed in. Well, the only thing that stayed in was this 3 and that 2. So this is 6. And I don't need to worry about absolute value bars because a cube root can accept both positive and negative. I don't have to guarantee that it's positive, unlike on a square root or a fourth root. So there is a rule that summarizes all this. And the acronym is EVO, EVO. You only have to worry about the absolute value bars when this exists. First of all, when it's an even index, like a square root or a fourth root or a sixth root or any kind of a root that is even. Plus also when the variable comes out and that variable comes out with an odd power. That's when you need to worry about the absolute value bars. So let's take a look at this next one. 18 x to the 4th y to the 6th. And we're just going to remember the EVO rules at the end. So this is square root. So the index of the radical is even. So I do need to worry about the fact that I might need absolute value bars, I might not. So let's deal with 18 first. 18 is 9 times 2. 9 is 3 times 3. So we know we have the 3 that came out. Let's leave some space, and then we know that a square root 2 stayed in. So that takes care of the 18. Now, what about x to the 4th? X to the 4th is x times x times x times x. We're looking for pairs because we're in square root, and here they are. So x came out and x came out. Okay. So x squared. Now, what about y to the 6th? I've got y times y times y times y times y times y. Now, I'm in square roots, so I'm looking for pairs. So there's a pair of y's, there's a pair of y's, and there's a pair of y's. So what also came out was y cubed. But now we need to worry about what do I need absolute value bars around? Well, was I dealing with an even index? Yes, I was. Okay. When variables came out, did any of them come out with an odd power? And yes, the y did. So I need absolute value bars around the y. So that would be my answer. Okay, the next one is also a square root. So let's deal with the 18 first. 18 is 9 times 2 again. The 9 is 3 times 3 again. So again, I've got 3, and I've got square root 2 on the inside. Now, if I have x to the 6th, and I group them up into pairs, that means I'm going to have x cubed that comes out with no other x's on the inside. Now, y to the 9th, this one might be good if I expanded this. Y to the 9th would simply be 9 y's. 1, 2, 3, 4, 5, 6, 7, 8, 9. And since I'm dealing with square roots, I'm going to pair them up. Four of them are going to come out, so that would be y to the 4th power, and there's an extra y that stays on the inside. Now, the last thing I need to do is worry about, does anybody need absolute values? Okay, well, it was a square root, so it was an even index. And did any variables come out with odd powers? And yes, this one did, the x did, so I need to put absolute value bars around it. And that would be the answer. Now, just to show you on the last one, I'm dealing with a cube root right here. So I don't need to worry about absolute value bars. Anytime the index is odd, you don't need to worry about it. So negative 54 would be negative 27 times 2. Now, negative 27, it would be really good if you learned your perfect cubes. Negative 27 is a perfect cube because it's negative 3 times negative 3 times negative 3. And the reason we like it as a perfect cube is because we're dealing with cube roots. So a negative 3 would come out. And it would join the positive 3 that's already out there. So I know I have negative 9 on the outside, and I know I'm left with a 2 on the inside. Now let's start dealing with the variables. X cubed, the cube root of x cubed, would simply be an x, because there'd be 3 of them, 1, 2, 3, of which one of them gets to come out, and it joins the one that's already out there, so that would be x squared. Now y to the 7th, 1, 2, 3, 4, 5, 6, 7. Group them up into groups of 3 because that's what cube root means. And here's a y and there's a y, so y squared gets to come out with a y that stays on the inside. And since this was a cube root problem, the index of the radical was odd. I don't need to worry about, does anybody need absolute values or not. And there's your answer.